Yo, what's up YouTube? Just want to say before I start this video, I cover about 6 problems. Problem from chapter 17 involving moment of inertia and reactions. Then we have a, velocity problem involving multiple moving points. Then we got something with relating gears and ratios, angular acceleration, angular velocity. Then we got an impact problem. I thought this problem was a really fun problem. It hits a ball, then hits at the wall, and then we want to find the angle and velocity after. Then we have this problem. It's a classic, transfer of energy problem with friction, with a bit of kinematics in here, so good throwback. And the first problem we do, this is a problem. It's just a, kinematic problem, but with non-constant acceleration, so it requires a bit of integration. So 6 problems total. All the problems, you'll have a blank worksheet linked in the description. You're welcome to try to do the problems before me, or you can watch along the video and see what I do and see the explanation. And I think this should help. Okay, going back to the beginning of how this class started, right? So, what do we got here? We got a particle moving along a straight line, where acceleration is a function of time. That's pretty nice. You don't want it as a function or anything else. Okay, and then you see that s is equal to 1. So, at t equals 0, it starts at some position, right? And it has some initial velocity. So this particle is already moving. It's like already somewhere along that line when you start looking at it, right? But our main goal is to determine the particle's velocity when its position is at t equals 6. So, some time's going to pass, and then we want to know where it is and the velocity at that point and how far it traveled. Okay. And maybe I should start by saying you cannot use kinematics for this because this is, acceleration is non-constant. It's not just a number. It's a function here. Okay. Well, what do we want to do first? What's the easiest thing? Okay, so we have acceleration. Why don't we find its velocity, right? So we know a is equal to what? A is equal to dv dt. Okay, so then we know that velocity is equal to what? Actually, I'll write it as this way. Dv, v to what? V final to v initial is equal to, what's this? This is going to be a dt. From t final to initial time, which is 0. Okay, so if we input our things here, we would see that it's going to become the velocity integrated from, okay, what's v final here? We don't know, so we'll just write it as v. What's VO? It's 2 meters. Okay. That's important to realize. Okay, a dt. It's the integral, and then times 0, from 0 to t. We don't know what the final time is. But we do know that our integrand is 2t minus 1 dt. Okay, so now if we take this setup here, we'll do this left-hand side first. It's going to be v minus 2, right? That's exactly what it becomes. It becomes v minus 2. That's it. And this is equal to t squared minus t from t to 0. Okay, I'm going to write this all somewhere else now. So we get v minus 2 is equal to t squared minus t. And then we can see that v is equal to, right, our final velocity v is equal to t squared minus t plus 2. Okay, so I don't have to solve for any initial conditions since I had bounds. That's a trick. I've seen a few people trying to solve for initial conditions. Yeah, you can do that, but this is just a faster way. Okay, now if I ask the questions like, what if t is what? If t is 6. Okay, now we can find the velocity at this point. So v of 6, it's going to be 6 squared minus 6 plus 2. So that's going to be 36 minus 6, which is 60. 60 plus 2. No, 36 minus 6 is 30. 30 plus 2 is 32. I don't know why I was saying 60. There we go. So this is your final velocity. Is this meters a second? Yeah. Okay, well that's one of your answers. Okay, let's do the next part. Determine the velocities. Okay, now we want to know the total distance it travels. Okay, so we said velocity is equal to ds dt, right? That's our relationship. Well, then we know that ds from some point s final to so is equal to the velocity dt from some initial time t to, from some initial time 0 to t. Okay, so what does this mean? Well, SF, we don't know what SF is, so we're going to leave it as S. Okay, we know what SO is. It's 1. So we're going to have 1 to S, and it's going to be ds. And this is all going to equal to what? Okay, so we had velocity as a function of time right here. So it's t. Okay, I got to restart this problem because there's a lot of people talking in the background. You can hear everything with my mic. Okay. So this integral, we're going to insert what v was. V is this. T squared minus t plus 2 dt. And then we're going to ask ourselves, what's the bounds here? So since this is our last integral, why don't we put for our top bound the top time, which is 6, and the bottom time, which is 0. Okay, so the left-hand side of this integral is just going to be s minus 1. And the right-hand side integral, it's going to be t cubed over 3 minus t squared over 2 and plus 2t from 6 to 0. Okay. So s minus 1 is equal to what? It's going to be, okay, and now I'm going to factor out a t here real quick. So t, I'll get t squared over 3 minus t over 2 plus 2. And then I'm going to insert 6 to 0 into this. So I know that it's 6, and then 6 squared is 36 over 3. Then minus 6 over 2, which is 3. Negative 3 plus 2 is negative 1. 36 divided by 3, I don't really know. Well, I do. Okay, so 30 divided by 10. 30 divided by 3 is 10. 6 divided by 3. Okay, this is 12, guys. Yeah, I did not see that for a second. 12 minus 1. I actually panicked right there. 12 minus 1 is 11. I legitimately forgot how to divide 36 by 3. Okay, now real quick. S minus 1, 66. What is this actually? So this is a distance. Let's read the question here. Determine the particle's velocity and the position at t equals 6 seconds. Also determine the total distance. Okay, so right now, when there's a change in time of 6 seconds, right? When there's a change in time of 6 seconds, we travel 66 meters. Okay. And initially, I'll just say we're at 1 meter. So we started at 1 meter. Okay. So the total distance traveled during this time is 66 meters. Okay. So we write this as ST, right? Norm ST. Total distance traveled is 66 meters. Okay, but then what about just position? Well then, okay, see how this is s minus 1 like I was saying? So, where are we actually at? Well, we are at what? S minus 1 equals 66, so s is equal to 67. So we're actually at 67 meters. That's where we're actually located. So if you had to put in your GPS, that's where you say. If someone asked you how far did you travel, when you turned on your GPS, you would say I traveled 66 meters since the time I turned on my GPS. So knowing the difference between these two answers is important. It's actually a big deal. All right. Okay, so we got this problem. Looks like we're going to use some sort of energy to calculate this, and then we're going to use some kinematics here, right? Okay, so what we can see is that initially, that's not how you spell initially, but it's fine, we'll leave it. So at A, right, I'll just erase it. Okay. So at A, what do we have? What forces, what type of energies and forces do we have? We have gravity, right, and we have, some initial speed. Okay. Right, so that's what we have, and then at B, we'll just say 2B, then we're going to have friction. Can't spell today. We're going to have friction coming in the way. And then at B, we're going to be at the tip. And then we're going to go to C. Right, and then we're going to be in the air. Okay, so that's kind of like the idea. So we have gravity and initial speed, and obviously there's weight of this involved here. And we're counting friction, and then boom, we're at a different speed, and then we're in the air. And we want to find this distance x. Right.
Yes.
God fucking damn it. Okay, so at A, right, let's use this equation. We use the change in energy equation. And then this will be at A to at B. Oh my god. Hopefully you couldn't hear all the yelling. Oh my god, me. Okay, so at T1, well, at A for T1, we have 1/2 mv, we'll call it mva squared. And then V1, what is V1? Well, V1 will be our gravitational potential energy. So the distance between this is 15 feet. Okay, so it's going to be weight times, I'll call it H1. Okay, I'm calling this H1, and I'm going to label this. Do not want to do that. Right. I'm going to call this H1. Then I'm going to call this H2. And then I'm going to call... Actually, I'm going to call this H2. Okay. So that's important, and then I'll just draw the free body diagram for points. So we have, right, we have our weight. And then we have the force of friction. We have a normal force. Okay, and then we would notice that our weight, so weight is equal to some weight in the tangential direction and weight in the normal direction. That's important. We'll talk about that stuff in a second, though. Okay, back to this stuff. Okay, what is T2? Well, T2 is going to be 1/2 mvb squared. Okay, and then coming into this, sorry, I made a minor mistake here. I gotta shift this. We have minus what? The force of friction times the change in position. Alright, so it's dragging around here. There's the friction here. Okay, so I'm going to call that change in S. So we have initial velocity, then V1, all of that stuff. And we're calling this point to be our origin just for this situation, right? So we won't have any sort of gravitational energy here. Okay, so our main goal is to find these components. Okay, so we want VB, right? That's the main thing we want. So I'm going to rearrange everything for VB. Where VB is going to equal to mva squared plus wh1. Give me a second. Okay, so I times everything by 2. In fact, I'm not going to skip steps. Usually I try to skip steps to make this go by fast. But I won't. Minus f, change in s. Then we're going to be multiplying this by 2 and then dividing by m. And then we're going to take the square root, the positive square root of this. Okay, so this is what we're going to get. And as you can see, we can simplify this a little bit more. So 2 and m, well, this is just going to be VA squared. And then this will be 2w over m h1. And then this would be minus 2f divided by m, change in s. Okay. So I'm going to find all these components. Now real quick, we already know that H1 is equal to 15. Okay. And then we know that our weight is 10. Now the force of friction, we don't know what the force of friction is. So the way we can, no, okay, so the force of friction, it's equal to mu k times normal force. Well, what is the normal force? Well, if we take the sum of the forces in the normal direction, so MAN, well, that's equal to 0, but it's equal to the normal force minus the weight in the normal direction. Okay, and I had it earlier, but I'm going to try to explain this better. Okay, so think about this, right? If this is a small angle, most of the weight should still be coming straight down, right? Like, I mean, the weight is always coming straight down, but most of the weight should be hitting at the normal plane instead of coming in the tangential plane. So we pick the bigger combination, so it's going to be 4 over 5 times the weight. 4 over 5 comes from the cosine, so it's the cosine of this angle times the weight. That is the normal. That is the weight in the normal direction. So 4 over 5 times 10, which is 8. So there's 8 pounds coming down in this direction. And then, you know, there's a little bit of weight coming. Well, there's less than 8 going in this direction. Okay. So that's the normal. So now we can come back up to here. And then mu k is 0.2. So 0.2 times 8. Well, that's going to be 1.6, right? Yeah. We have 1.6 pounds of weight. I mean, 1.6 pounds. yeah, pounds. Pounds is the unit for imperial. So we have this is our friction, right? This is coming and stopping us from going as fast as we can. So now we're going to fill in all the stuff for VB. So VB. Okay, VA squared is, well, it's 5 squared, which is 25. And plus, okay, and real quick, let's go up here. So weight. Weight is equal to mass times gravity. So then when we do weight divided by m, we just get gravity, right? So we'll have 2, and then gravity is 32. 2 times 32.2, right? 2 times 32.2 is 64.4. And then H1 is 15. Okay, and then we got 2, and then the force of friction, which is this. So 2 times 1.6. Okay, and then we got 1 over mass, right? So what is 1 over mass? Well, 1 over mass, that's the same thing as gravity divided by W, which is going to be 32.2 divided by 10. Okay, so in here we're going to write 10 times, and then 32.2 times 2, but we'll just write it right here. And then admittedly, I will admit that I calculated this thing, but I forgot my little change in S. But that's why I recommend always writing out this general form like this first, so you know where you messed up. But okay, so what is the change in S? The change in S is the distance it slides along around here. So this is a 3, 4, 5 triangle. So look at this. If the height is 15, so that's 3 times 5. So then this would be what? This would be 20, right? And then 5 times 5 is 25. And it's still the same angle for the same triangle. It's just a larger triangle. So we know that change in S is 25. Okay. So now if we put this into our calculator, and I'm going to do that now, we get this, 27.0814, and this is feet a second. So it's coming down at the speed. All right, it's coming down here. So this is all useful now, because now we can use our kinematics, and we can go back to physics 1, where things were nice and simple. All right, we can use that velocity. So I'm going to do this part in blue. Okay, so we want to find the distance x. So we know that VO, for us, in this case now, is 27.0814. then we know that the change in height, which we'll call what? We'll call it h2, I think we did, is going to be 25 feet. Right? 30 minus 5 is 25 feet. Okay? But we don't know what the change in x is. Okay, let's write down another thing. We know that gravity is 32.2. Okay. So we know that stuff. What else? Okay, well, we know that, and since we have a particle, we can infer a few more things. So we can use our kinematic equations. I'm going to write 3 of them out. So V is equal to VO plus AT. Another one is V squared is equal to VO squared plus 2A. And change in, we'll call it change in height for here. And the last one is change in height is equal to VOT plus 1/2 AT squared. So these are 3 kinematic equations, and we're going to figure out which one to use. Okay, so we want to know like what our x is. So we know that like since we're in the air, we don't have anything pushing us up. Like we're not in super advanced, dynamics where we have to worry about air resistance. So we know we have no air resistance, so we're still traveling at the same velocity coming this way. So that can help us, right? But we know that we're coming down to the Earth faster. Let's find this in terms of its components, because right now this is just coming down like that. But let's find it in terms of its components. Okay, so VOX, that is also equal to VX. And for us, it's going to be VO, and is it sine or cosine? Okay, so if it's sine, it will be a smaller angle, right? It'll be a smaller angle. If it's cosine, it'll be a larger angle. But earlier, we said we used cosine, right? We used cosine earlier, as you can see, to describe the weight in the normal direction. So, presumably, when we're talking about this tangential direction, if we shift our heads, right, we could imagine that we're going to use cosine here to describe, because now it's going to be the opposite. We're going to describe cosine theta. And for us, it's going to be VO divided by what? 4/5. And I'll put that in my calculator in a second. But then we know that VOY, which is just VOY, is going to be VO 3/5. And if I draw the diagram right here, right, this is it. Did not want to do that. Oh no, everything's flipping on me. So this would be VX, this would be VOY. Okay, and then we can infer the triangle carries over. Okay, so for these we get 16.249. And then what do we get for the other one? And then we get 21.665. Again, this is coming in this direction, and this is coming down in this direction. Okay. So should we assume gravity to be our positive direction? Yes, we should, right? We should consider coming down as our positive direction. Okay, so if all that's true, I'm going to use this equation because I want to use this. Okay. So change in height, we know what change in height is. The only thing we don't know is t. Okay, that's why I'm going to use this equation. The only thing we don't know is t, right? Okay, so change in height is 25. So 25 is equal to, and this is VO, but this is really going to be this right here. So it's equal to 16.249 times some t plus, and then A is going to be 32.2 divided by 2, which is going to be 16.1. Again, this will be positive because our velocity is coming down and gravity is also coming down. Okay. So then I'm going to insert this into my calculator, and I'll give you guys the quadratic of this, right? I'm going to give you guys what t is. Okay. And the answer I get for time, I get two of them. I get a -1, I get a +1. Definitely not going to use a -1. The +1 is 0.8. I'm going to call it 0.4 seconds. That's our positive time. That's the time it takes from it to go from B to C. So if we know that's true, now we can use our Vx velocity to find our change in x. Okay. So I'm going to do this part in green. Okay. So we know that V is equal to the change in x divided by the change in time. Vx. So we know change in x is going to be what? It's going to be Vx times change in t, which for us it's going to be 21.665 times 0.84. So our change in x, and I'll put this in my calculator and give it to you guys. And our answer is going to be 18.19. And this is units feet. Okay. So yeah, this problem, I like this problem. I like these types of problems because it's like the most realistic type of problem, and this is shit that I would do out there stepping off a roof and watch it roll off. Right. But so we had friction, we had gravity, and we could have used the other one. We could have used the equation for access. Maybe that might have been easier. I think this one was actually easier. Right? But I also like this problem because it involved kinematics. So you learned a lot in this one problem. Okay, so we got a impact problem here. This is... There will be a lot of things going on in this problem. This problem will be definitely not an easy problem. So we can see A is traveling with initial velocity, then it's going to hit B, and then B is going to have some velocity after it hits with A, and then B is going to hit the wall C, and then after that it'll travel with another velocity. And our looks like if we read the problem, we want to know the velocity of B after it hits the wall C. So again, there's a lot of things going on here. Okay. Now, if we know that each ball has a mass of 0.4 kilograms, that's the most, like, if that was not true, this problem would be 2 times harder already. But since we know that both of the balls have a mass of 0.4 kilograms, we know that this ball is going to transfer all that momentum into this ball. Okay. So, in theory, all that energy is going to go straight to the other ball, and A will become B, B will become A, right? Except reality will hit, and it'll have a little bit of a loss of velocity. But first, let's try to get as many points as we can by describing what VA is. So we have a ball A, and we know that it's traveling with respect to 30 degrees from the x-axis. So then we know that there's some velocity, Vy, and some velocity Vx, Vx, Vy. Now, for this whole problem, let's use the notation where this is the positive and this is the positive. So currently we're traveling in the negative direction. Okay. So if we think about Vx, Vx is going to be Va1 and then cosine 30. And then Vy is going to be Va1 sine 30. So Va1, it's going to be 5, and the cosine 30 is square root 3 over 2. We'll leave it like this. And this is going to be 5, and we'll leave it like that. So we're going to leave both of our answers like this for now, just in this most compact, concise form. In fact, we can write it a little bit better. It's 2.5 square root 3, and we'll write this one as 2.5. Okay. I usually don't like putting things into decimals, but this is fine. Okay, so that's the velocity that's coming in. So we know that VB x1 is equal to VB y1, which is equal to 0, right? It's initially not doing anything. So if we pull up our formula sheet here, hopefully you guys can see this right here. So we see that we're concerned about this stuff, right? And we're going to use this formula, and I'm going to copy it down. Okay. So, and our E is 0.8. Okay, and then this is going to be, I'll show you the formula again. It's VB2 minus VA2. And then I believe it's VA1 minus VB1. Yeah, it is. Okay. So this is what we have. Now, the only thing we know right now is VA1 and VB1, which initially VA1 was traveling with 5 meters a second. And then VB1, we know that's 0. Okay. So, now if we use this equation, okay, so if we use our equation, and by the way, also it has to be negative, because it's, right, we defined our, we defined our axes as this, so it's -5. So if we write the impact equation, it goes something like this. So we have mass VA1 plus mass VB1, and it's equal to the mass VA2 plus the mass VB2. And for us, we're lucky all of our masses are the same. So all we have to worry about is VA1 and VB1, which we know to be this to be 0, and this is -5. We get -5 is equal to, and like I said, all the masses can cancel out because all the masses are the same. It says it right here. So we get is equal to VA2 plus VB2. So we have 2 unknowns, but we have 2 equations to solve. Okay. So I like to do it this way. I'll write VB2 minus, okay, I'm going to write it under it. So if I put the -5 over here, -5 and times it by 0.8, -5 times 0.8 is -4. And then I get I get the stuff over here, VB2 minus VA2. So if I add this stuff up together, if I add these equations, I get -9. Okay, and then I see that there's going to be, the VA2s will cancel out, but I'm going to get 2 VB2. Okay, so I know VB2 is equal to -4.5. Okay, and if I know that's true, then I know VA2. We don't even need to write down VA2 because I'm pretty sure they're not even concerned about VA2, but we'll write it down anyway. So then we know that VA2, okay, I'll just show the work here. VA2 is going to be -5 minus VB2. Right? Just using this equation right here. So subtract VB2 on the other side. And then this is going to be -5 minus minus, so plus 4.5. So we get -0.5. So yeah, this thing is still rolling. VA is still rolling, but most of the velocity is transferred to V. Right? So remember in the beginning I said, in a perfect world, all of the velocity will be transferred, but in a non-perfect world, right? In a elastic, I believe it's called elastic collision. Yeah, so this makes sense. Okay, so VB2, we have that. Now, if we look at this diagram, when the balls hit each other, right, we have this diagram. So what I'm trying to say is that the momentum in the y direction, if it was like this, you know, it's pretty easy to do because the momentum in the y direction is the same as it is in the y direction and the angle is the same, so we don't have to do any sign. Now, the same idea applies about the velocity. The velocity in the y direction will be the same in the y direction, but the point is that the angle is going to change here, so there's going to be a change of angle. So I'm going to erase those diagrams. So the sum, and this is going to be with respect to y. Right. And I should label this as y prime. Okay, we'll call this y prime. So with respect to y prime, we have m we had MVB2. Right, we had MVB2. And then we also had, we're going to have MVB3. Now, these are just vectors right now. Okay, but let's put this as a speed and then times some sign. Okay, so it's going to be the sum of the mass and the... I'm actually going to get rid of the sum, because it's only one ball, so we don't have like a lot of moving parts here. So mass MVB2, and then sine 30, initial angle. And then apparently it's going to equal to the mass MVB3. We don't know what this velocity is exactly, but we know that it's going to travel at some velocity and at some angle theta. Okay, so we know that the masses can cancel, and VB2 sine theta, this is negative 9 over 2, right, 4.5, negative, same thing, times 1/2. And that's equal to VB3 sine theta. And I'll write this as negative 9 over 4. Okay. Now this is useful. You want to find VB3 and you want to find theta, and then we're done. Right? Then we're completely done with everything, and like life is good, right? Except we don't know everything yet. So we could use this equation. I mean, we can't use this equation, right? Because C is a wall. C is at the wall, so there's like no mass in the wall. Right? It's a wall. But we can use this type of equation again, and they want us to. It's hinting at that. So E prime is equal to 0.6, and then it's going to be equal to what? It'll be equal to VC2 minus VB2. So it's not going to be VB2. It's going to be VB3. My subscripts are all off today. VB3. And it's not. There's no such thing as VC2. It's just VC. And then, in this case, it's going to be VB2. And then here, it's going to be VC. Okay, and here I want to make a note to read this to you guys. Okay, so we see that if we use this coefficient restitution, it relates the relative velocity components along the line of impact, right? So that's kind of the important thing to say. And for us, the line of impact is not always going to be the x-axis, right? So I'm going to draw the collision for this, B hitting C. So I'll draw it up here. So C, then B is going to hit it, right? So that's the collision, right? Okay. Sorry, I said something wrong. The collision is along the x-axis. Earlier, though, when the balls hit each other, the collision was not, right? Right? The collision was not earlier, but for this one it is. So with that said, what we have to do here is we have to modify our equation and say with respect to x. Okay. So we modify this equation, it's going to be, by the way, in VC we know it's to be 0. Right, the wall doesn't move. Okay, and then VB3, it's going to be scalar velocity times cosine theta. Then divided by VB2, which is going to be negative 4.5 cosine theta. And it's cosine theta. For that theta, it's going to be cosine 30. Okay. So then we see that VB3 cosine theta, so this is a negative here, divided by negative, the negatives can go away. VB3 cosine theta is going to be this times this. So negative 4.5 cosine 30. So 4.5 cosine 30. Cosine 30 is square root 3 over 2 times 0.6. Okay. And that's the same thing as 9 times 0.6 times square root 3 all over 4, which is the same thing as 5.4 divided by 4. Again, just trying to conserve my decimals here. This is VB3 cosine theta. Okay. Specifically, remember this was the original theta, right? This is our new theta, and we want to find this theta, and we want to find VB. So, we have this, and we have this. Looks like we could say something. We could say that VB3, what we can do is pretty nice here. Is we can kind of combine things here. So VB3, and then we can do VB3 sine theta equals negative 9 over 4. And then we can also do VB3 cosine theta equals 5.4 square root 3. And what happens if we just divide these guys? Well, we get tangent theta is equal to negative 9 over 4, and then we get 5.4 divided by 4 square root 3. And then if we take the tan inverse, where theta is equal to the tan inverse of all that stuff, and I'll get it in a calculator for you guys. Okay, so we get negative 43.9 degrees. So if you were looking at a circle, and we'll just look at this diagram. It'll be from here and then down here. So look, it's literally following the diagram. Right. Okay, and then you can find your velocity, your scalar. I mean, you can find your scalar speed. Okay, I need some more space. Okay, and now we have what? So we'll use this to find VB3. So VB3 is going to equal to 5.4 divided by 4 square root 3. And then we're going to divide by the cosine, so we're going to have secant. And then we're going to put this angle in here. And then I'll give you guys this in a second. I'll put it in my calculator. Okay, so here's your answers. Get that and that. So there's a lot of things that was done in this single problem. So I thought this was a really good problem to do. But yeah. Okay, let's start this morning off with this problem. As we can see, when this moves, when RA turns like that, this will move, creating RB to move, and then when RB moves, it moves this F point P, and then the boat can move. So that's how this stuff works. If we read the problem, we can see that they want us to find the angular velocity of the propeller. So we want to find the speed at which this is accelerating. I mean, the speed at which this is rotating. Okay, and then we're given its acceleration. That's what we're given. And we know that it also starts at rest. Okay, so what we can use here is I'm just gonna write down a few relationships. We know that alpha d theta is equal to the same thing as w. Oh, we'll say omega dw. Right, that's one of our relationships, and then I'll write down a few more. And again, we may not use all these, but this is just stuff we can start with. It's always good to try to write out your options before you start the problem, in my opinion. There you go. Put my face over here. Okay, so we got all that, right? Now, what we want to really do is first realize that RA and RB are connected. So, whatever RA does, what something RB will do. And RA, okay, so we can say RA is proportional to RB, right? They're proportional to each other. Let me draw that a little bit better. Proportional. This means proportional. But more precisely, we know that RB is equal to 2 RA, right? So RA is a smaller radius. Okay. So if we know that the drive shaft, this is the drive shaft, I believe, right? gear A on the drive shaft. So we know that this will be having this acceleration over this amount of time. And then we could transfer it to RB, and then RB will tell us at P, right? Okay. Then, so obviously RA and RB are proportional. That means that they will have the same velocity and the same acceleration. And I want to show you guys these formulas, right? So what we can use is we can use these types of things right here. But before we use them, let's just use this, okay? So for A, okay, now this is for object A. If we split the differential, so if we times this out, we'll have dW is equal to alpha dt. Let me make that look a little bit more like alpha. Okay, and then if we integrate both sides, right, and we know that it starts at some time 0 and ends at some time 1.3, right, for both. By the way, there's the bounds for this one is just going to be w to 0, my bad. So this would be omega is equal to, and then the bounds for this one is going to be 1.3 to 0. Okay, this is the initial time, this is the ending time, and it tells us. That's why we can use these bounds. And then we're going to insert the alpha function into here. So 300 square root t dt. And then we could see that this is going to become 300, and I believe square root 3, well, this would be 3 halves divided by 3 halves. All inserting from 1.3 to 0. So if all that's true, then we can sit, and I should label this now WA. That's going to be 300 divided by 3, which is 100. 100 times 2 is 200, so we'll have 200, and we'll have T, so the 3 halves, 1.3 to 0. Okay. And then now I'm going to put this stuff in, but I could actually hold off. I don't need to, calculate this initially right now. I could just hold off for now. Okay, so this is WA, right? And we know that we can relate RA, WA, right? RAWA is going to be nearly the same. It's going to be the same thing as what? W. Okay, so it's going to be the same thing as RB, WB. So I said something a little bit wrong earlier. They're not going to be they're not going to be spinning at the same speed, but we can relate them using this one speed, right? So then we can see that WB is equal to what? RA, WA divided by RB. And then that is going to be, well, RA is 0.7, RB is 1.4, so it's going to be 0.7 divided by 1.4, which is 1/2. And then WA, we'll put this stuff over here now. And we'll have 200 T to the 3 halves, going from 1.3 to 0. And then we could write this a little bit faster as 100, and we'll write T to the 3 halves, 1.3 to 0. And now we can compute this. Okay, and here's your answer. So I know that this problem wasn't that hard compared to the other problems, but I thought it was still a good problem to do to show the relationship between gears and angular velocity, right? So if we had this problem on the test, it may be a little bit harder where they ask us to find accelerations to, or if they give us the acceleration over here, or if they give us the angular velocity over here, and then they want us to find the acceleration over here, right? So this relationship worked nice because it worked its way down, but it could always start from here and work its way up, and it would be the same process. Yeah, this second type of problem is actually one of my favorite problems, and I'll show you the faster way of doing these types of problems rather than maybe the way that you're doing it currently. Okay, so we have a link, right? Link AB, and we see that it's rotating up. So if it rotates up, then C, it's sliding in this horizontal plane only. It's going to be pulled this way. Okay, and what we want to know is we want to determine the velocity of this block and the angular velocity of BC. So right, this is rotating out, right? BC as a whole has rotation, but only point C moves horizontally. And then we want to sketch the positions. Okay. So the relationship that we can use is we can use this information to find this information. And what that looks like is what we can do is we can see that VB is equal to VA plus omega AB cross R B to A. Okay, and then we know that VA is 0, so VA doesn't move. And then we know that this is going to be 3. And is it positive 3 or is it negative 3? It's positive 3. It's counterclockwise, right? And let me just write that. Positive omega. If it was the other way around, you got to write negative omega. That's you got to make a deal out of it. And RB to A is the same thing as RA to RB, I believe. No, I'm pretty sure. So then you write this position vector. What's this? So you go from RA to RB. And you'd see that that's 0.5 cosine 30. I mean cosine 45, which is root 2. And then the other one is the same thing. So 0.5 root 2 over 2. And I'll simplify this a little bit. I'll write this as root 2 over 4. Because that's what it is. Right? Root 2 over 4. Okay. And again, this is going up and then going up. Okay, so we got everything we need, so we can find what VB is here. So, and since we're taking a cross product, I can instantly jump to this, right? It's going to be 0, 0, and then omega is going to be 3. Okay, and then we can insert this stuff in. Okay, so now if we take this, we're going to get some, I write my vectors as columns. I recommend you do it too. It makes things a lot easier and simpler. So 0, that's 0. Then minus 3 over 4 square root 2. And the next one's going to be this, but then minus this and this. So minus 3, 4 square root 2. Okay. These zeros make things nice, right? And the last one's going to be 0. Which makes sense, right? VB can't move in the K direction. It can't come at us. It's stuck moving this way only. It can't come at you. So we know that VB is equal to, it's going to be this vector, which I'll clean up, negative 3 over 4 square root 2. And then this one will be 3 over 4 square root 2. Okay. So that's good to know. You know why that's good to know? Because now we can do something again that's kind of similar. Where it's going to be like this. We want to find VC, right? So VC is equal to what? VB plus omega BC. Then this is going to be plus. And remember we had VB, VA, and that turned into BA. So for us it's going to be RC, and then A is the second one. So B should be the second one right here. Okay. And all we got to do is find out what RC, RB is. So RC to RB, RC with respect to B is the same thing as RB to RC. So from B to C, they get just 1.5 horizontally. So we can write this new vector. And real quick, since we see that VC can only move in the horizontal plane, we can only write a VC here. So we're going to write it right here. And you could insert a negative now because you realize that it's going to have to move this direction. You don't have to, right? But then you're going to get a negative in the end. So I won't do that. I won't insert a negative yet. But if you want to jump ahead, you could insert a negative. Sometimes I do. But you don't need to. But what you should realize is you insert a 0 for the J component, the Y direction. Okay, and then VB, write VB here. negative 3 over 4 square root 2, 3 over 4 square root 2. And then plus, then now you gotta take this determinant, and you don't know what WBC is, so you just write W. Alright, that's all you do. And then RCRB, yeah, it's just gonna be 1.5. Okay, so then what you get is you, okay, so I will write this part out right here. So you're gonna get this vector. As you can see, 0, 0, so there's no I component. And then 0, this, so there's only going to be a j component. It's going to be negative, negative, 1.5 omega. And again, no k component. So now when you add these guys together, you're going to get negative 3 over 4, square root 2, minus minus, plus 1.5 w. My bad. This is the I component. You would add 0 to this. So this plus this. This vector right here is the product of this cross. Okay, now you add this one to this, my bad. 3 over 4, square root 2. That's going to be plus 1.5 omega. Okay, so now you can use these relationships, and you see that VC has to equal to this, and then you could solve for W. It actually works out really nice. So VC is equal to negative 3 over 4 square root 2. And that makes sense because it's saying that it's going down in this direction, right? So this is your answer. It would make sense. But if you want to get rid of that negative, you could write it like this. VC is equal to 3 over 4 square root 2. And then you indicate the direction. My bad, that's the positive direction. You indicate the direction. Like that. And I usually that's how I usually write my test answer. It's like I'll write it as a positive and then indicate the direction. Just so there's no confusion. Okay, and then you can solve for omega now. So you'd see that 0 is equal to 3 over 4 square root 2. And again, I'm just solving horizontally here. That's why I like doing this method. You get to solve horizontally and vertically really nice. Plus 1.5 omega. So we can see this is going to be 3 over 4, negative 3 over 4 square root 2. And it's going to be equal to W. And then 1.5 is 3 over 2. So then if I times this by 2 over 3, and then we can see that 3's go away, and that we'll get omega is equal to, so this is going to be 1/2. So negative root 2 over 2, which is the same thing as negative 1 over root 2. So we could see that omega is equal to 1 over root 2, but it's going in the what? It's going in the counter. I mean, it's going in the clockwise direction. And this is in rads a second. Again, so it's just about stating your orientation. And also, real quick, let's not just write omega. Let's write what type of omega it is. It's omega BC. Okay, there we go. And I'm going to make more space to do the sketches now. Okay, so it's time to do some sketching. Okay, so I'll just draw out this completely 3 times, right? So we have A, and I want to know about the position of link BC. Okay, so they're just really actually just changing this angle. It's actually not that bad at all. So you just write 60, and then indicate that BC. All right, so if this angle gets bigger, then it's going to kind of have like this little mini angle. And C is still stuck horizontally. Right? So if you increase this angle, then this thing is coming up, right? And then that's why there's this other angle that will correspond to it. Okay. And then same thing again. 60. Oh no, it's not 60. I want to see. Oh. I don't even know why they want. Okay, like I'm not going to. There's really no need for me to draw this at 45 degrees because they did it for us. So I'm going to draw it at 30 degrees. So at 30 degrees, this is lower. So then you'd actually see that there'd be a kink downwards, right? Something like. Let me try to draw this a little bit better. So this is going to be pushed down, right? So if it's pushed down, then it would be like this. I don't know where the extra bend came from. So if it's pushed up, there's this bend. So I'm trying to logically think about how to draw this. Like, okay, 30 degrees. It's going to be like this. Okay, like it's being pulled down, right? I don't know why I can't, like, this is accurate. Okay, trust me, this is accurate. It just looks terrible. Like it's being pulled down, and you should indicate that B is coming down like that, and that B is going up like that. And then literally, I mean, this is the perfect description for 45 degrees. So just leave it there. Okay, real quick before we go into this problem, I just want to state that in the beginning of this problem I wrote r equals distance and it's equal to 0.25. Don't, that's not true. It's equal to 1/8. I'll let you later on see that I correct this mistake. It's a minor mistake. I never actually factored this in, so everything is correct. I just wrote this number wrong in the beginning for some reason. Okay, admittedly, this next problem will take a while. It may be the hardest problem we do. It is one of the last chapters, so that should be expected. Okay, if we read this problem, it's really not asking for that much, but to get the initial acceleration and the vertical reaction at A, they're going to have to do a lot of things to get to there. Okay, now notice that we're saying that this block is originally in equilibrium, right? So pretend that you had your finger here. You had your finger right here, and you're holding it up. And then you take your finger away, and then everything starts to accelerate. Right? It's going to fall down. So that's the idea of this. Okay, so with that said, let's write down some formulas that will our goal. Now I'm going to make kind of a jump cut, and I'll show you guys. Here's the formulas. You can find this in the back of the book if you want, or online. Search it up. Dynamics cheat sheets. You should be able to find it. Okay, so you're going to notice that I made kind of a jump here, and I put a lot of formulas down. Now the reason why is because I don't want to write down and waste a lot of time. I don't want to be wasting a lot of time later on. So we're going to use the sum of the moments with respect to A, so at this point. And then we're going to take the total moment of inertia. The reason why is because to find some of the moments, we do need IA. So we're going to have to find the moment of inertia. And then we're going to use IA to later on find this stuff too. I mean, we're going to use some of the moments A to find this stuff later on. So I'm going to deal with that. But before I do that, let me draw a diagram to actually show you guys what's going on here. Okay, so like I've been saying, your finger's here. And then when you take your finger off, this thing is going to swing, right? It's going to swing forward. Swing this way. So, if you have the box, and then you see that, like, if we're swinging this way, this is your motion, then the normal reactions at A, right, it's going to be to resist that. So it's going to be in the opposite direction. Right, so that's going to be your AX and AY. That's your normal reactions here. Okay. And then, since we want vectors, we could try to examine this, right, as this and this, right? And then dot, 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 dot. So, like, your real vector, like your actual vector, and this is its components, this is MAT. This is the object swinging. This is its motion. And you don't have, like, the normal, you don't have MAT and MAN, because MAN is 0, right? But you have MAT, and you can describe MAT in two directions, along the x-axis and along the y-axis. Okay, so this is your free body diagram, but we're forgetting one more thing. We should indicate that the weight is pulling down. Right, so there we go. Okay, so we're going to take the original sum of the moments. So right now, at this moment, like, we're going to think about what is the moments at A. So really, all at this moment, all we do is we have the weight, and the weight's just pulling us down, right? And it's going to force us to go in this, this is a clockwise circle, right? So then we know it's going to be minus W, right? Because weight is our only true force, right? weight is our only true force, and MAT just stands for the motion of the force, right? We're not applying MAT. We're not applying a force. That's why I drew this stuff in green. The only force that's acting is gravity. All right, that's the only force there is. So it's going to be the weight, and it's pulling. If you have this, like, if you're thinking about this, it's pushing it down, right? Pushing it down in a clockwise direction. And we take gravity to be at the center of mass. For a square, it's a lot easier, so it's right here. What's the distance right here? What's the radial distance between the center of mass and A? It's 0.25, so we can write those 1/4. Okay, and what's the weight? The weight is 24 kilograms. So we have negative 24, and then gravity, we'll call it G, or 1/4. Okay, and then 24 divided by 4, ooh, that's 6, negative 6G. We'll write this as negative 6G. Okay. So we want to find what IA is now, so then we can solve for alpha. Okay, so let's solve for, let's do this stuff. Okay, IG. So the center of mass, not the center of mass, the moment of inertia with respect to the center of gravity, and then plus the parallel axis theorem. So if I pull this up, and we're going to go to a square. Don't I have one here? Okay, so the thin plate, right? The thin plate. That's what it is. It's a thin plate. The center of mass, so IZZ, that's the one where it's going to be 1/12 m a squared b squared. Okay. And then the parallel axis theorem says we have IG, then just add plus MD squared. Okay. Okay, and then notice the cut here real quick. Okay, so I made this cut because I wanted to show you guys that D is important. You need to find D correctly. So when we want to find D is this, like, the distance from A to G. G is right here. Okay, and I'll even write G here. So what we do is we want to find the hypotenuse distance here. Okay, and this is important because these distances we know, it's 0.5 and 0.5. D we don't exactly know, and we need it for the parallel axis theorem for it to work. So if we use Pythagorean's theorem, we can see that we get 0.25 squared plus 0.25 squared. And that is equal to what? That's equal to D squared. And we want D squared. So let me just write this out. So this is 1/4 squared times 2. And that's 2 times 1/16, which is 1/8. So D squared is 1/8. Okay. Now A squared plus B squared, we'll write it over here. A squared plus B squared. A and B are the same thing. They both are the same thing. So you can just do 2A squared. And then you could say that A is 0.5. So 2 times 1/2 squared. That's going to be 2 times 1/4, which is 1/2. Okay. So you have mass. So you can factor out the mass here real quick. And then you're going to have 1/12 times 1/2. Then plus, and then this is going to be 1/8. Okay, so what do you have? You're going to have mass, and then this is going to be 1/24, plus, and I'm going to write 1/8 as 3/24. Okay, and then, look, mass is 24 itself. So I'm going to erase m and write 24. So as you can see here, this cancels, so we just get 4. The moment of inertia, like, and let me write, instead of IG here, let me write IA. Sorry, this should be IA total. This here is IG. This is IG, and then right here is the parallel axis theorem being involved in it. So we get 4. That's a really nice answer. Okay, so we know that using this idea, we can say that alpha, so we want alpha alone by itself. Alpha is equal to this, negative 6G, divided by IA, which is what we have right here. So divided by 4. So we get that alpha is equal to negative 3/2 gravity. Okay. So let's put that in a decimal. So when you put this in your calculator, you get alpha is equal to negative 14.715. And what is this? This is radians a second squared. So what you could say that alpha is equal to 14.715 radians a second squared. In the what direction? In the clockwise direction, right? So either one of these is your answer. I mean, I usually pick the second one because it looks cleaner. Okay. So there you go. You already found one of your answers. You want to find, but you need the reactions now. So I'm going to make some more space real quick. Okay, so I had to take a screenshot of this and put it here. Or else everything was going to delete. I couldn't shrink it. Okay, so now we want to find the reactions. So we want to find AX and AY. What are those? Okay, well, what can we use? We can use the fact that we can use the sum of the forces. That's the thing we can use. So sum of the forces, and we're going to take them in the X and Y direction. Okay. MAY. Now, before we move on, we should state the fact that we have our reaction forces pushing up. Pushing to the right. Yeah, to the right, and pushing up. Okay, so MAX, right? Okay, for MAX, what do we got here? So we have our negative force going in this direction, right? So MAT, and then we want it along the x-axis, so cosine 45. And we're saying that this is equal to AX. Okay, now let's define what MAT is. So M we know is to be 24. AT, alpha R. Now, alpha is going to be this number. So negative 14.715. Then what is R? Okay, now real quick. I just realized this now, that this D is 1/8. I mean, this D squared is 1/8, right? R is equal to the same thing as D. I don't know why I wrote that earlier. That's like me. That's wrong. Up here, what I wrote. So I got to erase this. That's a big no-no. So R is equal to D. Because remember I said D is this thing between A and G. Like earlier, I don't know why I wrote that. That's terrible. But we know that D is what? D is the square root of 1/8. Okay. Right, that's what we know. Because this was D squared here. So my bad on that earlier. That's kind of a big deal. Should have not wrote that. Okay. So now we're going to put 1/8. Not 1/8. Square root 1/8. Okay. So we have mass, acceleration. Acceleration is alpha times R. And then we need cosine 45, which is square root 2/2. Okay, there we go. So I'm going to compute this number over here. And I'll give it to you guys. And then when you do this, look, you get 88.29 newtons to the right, which makes sense, okay? As for the second part, it's going to be nearly identical. So MAY you can describe as MAT sine 45. And then for this, we're going to have our reaction upwards, positive reaction, so AY, and then minus the weight. Okay, so then in general, we're going to have AY is equal to what? The weight minus MAT sine 45. Okay, so then the weight, it's going to be what? It's going to be 24 times 9.81, and then minus, see this guy right here? This is identically equal to this over here, right? Because cosine 45 and sine 45 are the same thing, so you could reuse this number. So minus 88.29. And I'll put this in the calculator and tell you guys what AY is. Okay, so then AY is this. Here we go. That's AY. So that's a nice answer. And it shows that we're going to have a pretty large reaction upwards, right? Because we have gravity acting down on us. So we need a lot of force to counteract, right? So you found this problem I thought was really interesting because you have to use moment of inertia. And then you have to use, your tangential normal forces. So some kinetics in here. And then you kind of go back a little bit into like statics and you think about reactions and things like that. So I thought this was a good fun problem and summarized most of chapter 17 and what we'll see on the test, hopefully.
Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up in the algorithm.